World of particles. The tiny bits that make up, well, everything. And wow, you guys sent us a ton of stuff about this. Everything from like the basic what is an atom stuff to some serious physics theories.
Yeah, it's a pretty big universe, even when you're talking about the smallest things in it.
That's what I love about this topic, though. It's like we're going to zoom in from the everyday world, the stuff we see around us, all the way down to this tiny subatomic realm. And who knows what we'll find along the way.
Well, we'll definitely encounter some mind-boggling ideas, but we'll try to keep it clear, concise. I promise no one's getting lost in a physics textbook today.
Exactly. It's a journey. And to kick things off, we're starting with, I guess, a familiar character in this tiny world, the electron. Everyone's heard of electrons, right? But what's their story in this subatomic world? What makes them so important?
Okay, so electrons, right. They're these negatively charged particles that basically just zip around the nucleus of an atom.
Right, the nucleus, that's where the protons and neutrons hang out, right?
Exactly. And compared to those guys, electrons are super, super light, almost like negligible in terms of mass. But here's the thing. They don't just act like little tiny balls of matter.
Hold on, I've heard about this.
Yeah.
They're like waves too, right? That always messes with my head a little bit.
Yeah, it's one of those quantum mechanics things that just kind of bends your brain a little bit. We call it wave-particle duality. It's like, how can something be two things at once,
So how do we actually wrap our heads around this wave-particle thing? Help me out here. It can't just be some physics trick, right?
No, it's not a trick, I swear. It's actually fundamental to, how atoms work. You see, because electrons can act like waves, they don't just orbit the nucleus like planets around the sun. It's more like they exist in these cloud-like regions, kind of fuzzy, We call those orbitals.
Okay, so fuzzy clouds instead of perfect little orbits. Kind of like that. It's less, I don't know, rigid.
And these orbitals, they have different shapes, different energy levels. And it's those energy levels that really determine how atoms bond and form, well, everything, really. Molecules, materials, all of it.
So it's like each electron has its own, I don't know, vibe, its own energy level that sort of dictates how it's going to interact with other atoms.
That's a great way to put it. And to keep track of all these different vibes, the energy levels, the shapes of the orbitals, physicists use these things called quantum numbers.
Quantum numbers. All right, that's sounding a bit Star Trek-y now, but I'm with you.
Yeah, it might sound kind of complicated, but think of it like this. Imagine, a big, bustling city with tons of buildings. Each electron in an atom is like a resident in that city, each with a unique address.
Okay, I can see where you're going with this.
So the quantum numbers are like the street, the building number, the apartment number. They tell us exactly where that electron lives within the atom.
So electrons, each with their own unique address in the atom's bustling city. Love it. But hold on a sec. We started talking about electrons, but what about those other guys in the nucleus, the protons and neutrons? What's their deal? What are they made of?
Okay, now we're getting to the really good stuff. Protons and neutrons, they're not like the most fundamental particles. It's like those Russian nesting dolls. You open one and there's another one inside.
I'm intrigued. Another layer to this.
So inside protons and neutrons, we find these even tinier particles called quarks.
Quarks. Okay, the name alone sounds pretty fundamental. And what's keeping these quarks all bundled up together inside the protons and neutrons? It must be something pretty powerful to create those guys.
It is. We're talking about one of the strongest forces in the universe here, the strong force. It's like the super glue of the subatomic world binding these quarks together.
Wow, super glue. That's intense. So this strong force is what keeps the nucleus of an atom from just, flying apart.
Exactly. It's that strong force that's holding everything together in there. And it's so strong that quarks are actually never found alone, like ever. They're always confined within these larger particles, the protons, the neutrons,
So no rogue quarks roaming around the universe. That's kind of wild. Why is that?
Imagine this. Okay, you're trying to pull apart two really strong magnets that are stuck together. The more you pull, the stronger that attraction seems to get, right?
I can picture that, yeah.
It's the same with quarks. The more you try to separate them, the stronger the strong force becomes. So they're basically like forever bound together.
That's incredible. So we've got these tiny quarks forever bound together by this insanely strong force forming the protons and neutrons, the core of the atom. It's mind-boggling how much is packed into something so tiny.
Right. And speaking of tiny things with big effects, remember we mentioned that Higgs boson earlier?
Oh, yeah, the God particle. It's the one that was all over the news a while back. It's the one that gives other particles their mass, right?
That's the one. It's like the universe's mass distributor. The Higgs boson interacts with other particles, including those quarks we were just talking about. And it's that interaction, that's what gives them their mass.
Whoa, okay. So no Higgs boson, no mass for those particles. Everything would just be zipping around at the speed of light.
Pretty much. Without the Higgs boson, atoms wouldn't even form, stars wouldn't exist. The universe would be a very, very different place.
So much depends on these tiny, invisible particles. It makes you wonder, what else might be lurking down there in the subatomic world that we haven't discovered yet?
That's the beauty of particle physics. The more we learn, the more we realize how much more there is to discover.
Well, my mind is already blown, and we've just scratched the surface. But before we go any further, can we, step back for a second? I'm trying to wrap my head around all these interactions between particles. Is there, a rule book, something that explains how it all works?
Of course, of course. We have theories like quantum electrodynamics and quantum chromodynamics. They provide the framework for understanding how particles interact.
Okay, I'm going to need you to break those down a bit. Those are some serious tongue twisters.
No problem. Let's start with quantum electrodynamics. We usually just call it QED.
QED. Okay, much easier.
It's essentially the rule book for how electrons and photons, those are the particles of light, interact. And it's incredibly precise. It's been tested and confirmed countless times.
So QED explains how light and matter interact at, the most fundamental level.
Precisely. And then we have quantum chromodynamics, or QCD for short. That one's the rule book for how quarks and gluons behave. Gluons are the particles that carry that strong force we were talking about.
So QCD is all about the nucleus, the strong force interactions.
You got it. It's a bit more complex than QED, but it's crucial for understanding how the nucleus works.
Okay, so if we think of this subatomic world as our bustling city, QED is governing the traffic between electrons and photons, while QCD is handling the interactions between quarks and gluons, like two sets of rules for different parts of the city.
That's a great analogy. And to help visualize all these complex interactions, physicists use tools called Feynman diagrams.
Feynman diagrams. Okay, tell me more. Are those little maps of particle interactions? I'm a visual learner, so any visuals help.
You could say that they're like little cartoons almost that represent how particles interact, how they exchange energy, momentum, all that. It's a way for physicists to communicate these interactions without getting bogged down in super complicated math.
So it's like a secret language for physicists, helping them make sense of these tiny particle interactions.
Exactly. And these interactions, governed by QED and QCD, they're really the foundation of our understanding of the universe at its most fundamental level.
This is amazing. We've gone from everyday stuff to quarks, gluons, these powerful forces that hold them together. It's like a whole hidden universe within our own.
And we've only just started. There's so much more to explore in this vast, mysterious world of particles.
Lead the way. I'm ready for more.
All right. Next up, we'll step into the realm of the standard model of particle physics, which is the big picture, right? It encompasses all the known fundamental particles and forces. But even this model, as successful as it's been, well, it might be just a piece of a much larger puzzle.
Intriguing. So the standard model, it's our current best map of this subatomic world, but we suspect there might be unexplored territories out there.
You got it. There are things happening in the universe that the standard model just can't quite explain. Things that hint at new particles, new forces beyond our current understanding.
This is getting exciting. It sounds like we're on the verge of, discovering new physics.
We are. And the search for new physics, it's one of the most exciting frontiers in science. We'll explore some of those ideas like supersymmetry, string theory. We'll talk about how scientists are actually searching for evidence of these new phenomena.
Supersymmetry, string theory. I've definitely heard those terms thrown around, but I need that layman's explanation. Break it down for me.
All right, let's start with supersymmetry, or SUSY for short. This one proposes that basically every known particle has a partner particle. It's like a super partner, but with different properties.
So a mere universe of particles that we haven't discovered yet.
Kind of. These super partners, they would interact differently with the forces of nature. And if we find them, they could be the key to solving some of the biggest mysteries in physics, like the whole deal with dark matter.
Okay, SUSY is definitely sounding pretty wild. But what about string theory? That's the one that says everything is made of tiny vibrating strings, right?
That's the one. Imagine zooming in even further, way past the quarks and electrons, and you find these tiny vibrating strings. The way they vibrate, that determines the properties of the particles we see, like how different notes come from different vibrations on a guitar string.
So instead of a universe of little billiard balls bouncing around, We've got a universe of tiny vibrating strings. That's a big shift in how we think about things.
It is. And string theory, it gets even wilder. It predicts the existence of extra dimensions beyond the three spatial dimensions that we experience, up, down, left, right, forward, back.
Extra dimensions,
Hmm?
like parallel universes or something.
Not exactly parallel universes. It's more like, imagine these extra dimensions as tiny, curled up spaces that are all around us, but just too small for us to detect.
Okay, so according to string theory, we're basically blind to these extra dimensions. That's pretty mind-blowing.
Yeah, and these extra dimensions, they're actually essential for string theory to work. They allow for this idea of uniting gravity with all the other fundamental forces, something that has been like the holy grail for physicists for a long time.
So string theory wants to be the, ultimate theory of everything, unifying all forces, all matter, under one elegant framework.
That's the goal, but it's incredibly complex, and we haven't actually proven it experimentally yet.
String theory definitely wins the award for most mind-bending theory so far. But whether it's string theory, supersymmetry, or some other theory we haven't even imagined yet, it's clear that there's a lot more to the universe than meets the eye.
Absolutely. And that's what makes physics so exciting. There's always something new to discover, a new mystery to unravel.
Well, I'm ready for the next layer of the cosmic onion. What else awaits us on this deep dive?
Now that we've, gotten a feel for the subatomic world, let's zoom out and see how all these tiny particles actually shaped the vast universe we see today. We'll talk about the Big Bang, the formation of the first elements, and how those mysteries of dark matter and dark energy play out on a cosmic scale.
From the smallest to the largest, this deep dive keeps getting better and better.
All right, so before we go too much further down this rabbit hole, let's talk about the standard model we keep bringing up. It's kind of like, the periodic table, but for all the universe's tiniest ingredients.
Yeah, I remember you said it's like super successful, but maybe also incomplete. That's kind of a weird combo, right? What makes it so great, but also where does it sort of fall short?
Well, think about it like this. The standard model, it's elegant, it's organized, and it's made predictions that we've actually proven correct, like over and over again. It basically lays out all the fundamental particles, things like quarks, leptons, and the forces that govern how they interact, things like the electromagnetic force, the strong force.
So it's the ultimate recipe book for the universe.
Yeah, that's a good way to put it. But even the best recipe book, sometimes it can have a few gaps.
What do you mean?
Well, the standard model, it doesn't explain everything. Like, for example, it doesn't include gravity.
Wait, seriously, gravity? That's kind of a big one to leave out, isn't it? I mean, gravity is what keeps our feet on the ground, keeps the planets in orbit.
Right, exactly. And it's a big puzzle that physicists are still trying to figure out how to fit gravity into this whole picture. And there are other mysteries, too, like dark matter and dark energy. The standard model doesn't really account for those, and they make up a huge chunk of the universe.
Okay, hold on, back up a second. Dark matter, dark energy. Those sound like, I don't know, something out of a sci-fi movie.
I know, right? They sound pretty wild, but they're real, I promise. We know dark matter exists because we can actually see its gravitational effects on galaxies. It's like this invisible scaffolding that's holding the universe together.
So it's matter, but it doesn't interact with light. Like we can't see it, touch it, even detect it directly.
Exactly. And then there's dark energy, which is, if possible, even weirder. It's this force that's actually causing the expansion of the universe to, speed up.
Wait, speed up? I thought things were supposed to be slowing down after the Big Bang, like the initial explosion and all that.
You'd think so, right? But nope, the universe is actually expanding faster and faster, and dark energy is the culprit we think is behind it all.
That's kind of freaky.
Yeah.
So it sounds like the standard model, it's great for explaining the stuff we can see, the stuff we can interact with, but it's missing a big piece of the puzzle when it comes to, the universe as a whole.
Exactly. And that's why physicists are always on the lookout for what lies beyond the standard model, right? What's missing from our current understanding. There are a lot of theories out there, and some of them, well, they get pretty mind-blowing.
You already kind of teased supersymmetry and string theory earlier. Let's dive into those. Give me the SparkNotes version, the explanation for someone who didn't major in theoretical physics.
Okay, let's start with supersymmetry, which we often just call Hess-USY.
Hess-USY, got it.
Basically, it proposes that for every known particle, there's a partner particle, like a superpartner, but with different properties.
So like a whole mirror universe of particles we haven't discovered yet.
Kind of, yeah. And these superpartners, they'd interact differently with all the forces of nature. And if they exist, they could be the key to solving some of those big mysteries we were talking about, like the whole dark matter thing.
Okay, SUSY is definitely up there on the weirdness scale.
Yeah,
What about string theory? That's the one where, like, everything's made of tiny vibrating strings, right?
you got it. Imagine you could zoom in even further than we have, way past quarks and electrons, and what you find are these tiny vibrating strings. The way they vibrate, that determines the properties of the particles we see, kind of like how, different notes come from different vibrations on a guitar string.
So instead of a universe of, like, little billiard balls, we have a universe of tiny vibrating strings. That's a pretty big shift in perspective, isn't it?
It is, and string theory, it gets even, more out there because it predicts extra dimensions, like beyond the 3 dimensions we experience every day, up, down, left, right, forward, back.
Extra dimensions. Wait, are we talking, like, parallel universes here?
Not exactly parallel universes. Think of it more like these extra dimensions are these tiny, curled up spaces that are all around us, but they're just too small for us to actually see or detect them.
So string theory says we're basically, like, blind to these extra dimensions. Man, that's hard to wrap my head around.
I know, right? But these extra dimensions, they're actually really important for string theory to work. They kind of make the whole thing make sense. Like, they allow for this idea of unifying gravity with the other forces, which has been a huge goal for physicists, trying to bring all those forces together under one unified theory.
So string theory is trying to be the, like, ultimate theory of everything, uniting all forces, all matter under one elegant framework.
That's the ambition. But it's super complex, and it hasn't been experimentally proven yet, so it's still, in the theoretical realm.
Okay, string theory definitely wins the award for most mind-bending theory so far. But whether it's string theory or a SUSY or some other theory we haven't even thought of yet, it sounds like there's a lot more to this universe than, what we can see and touch.
Absolutely, and that's what makes physics so exciting, right? There's always something new to discover, a new mystery to unravel.
Well, I'm ready for the next layer of the cosmic onion. What other wonders await us on this deep dive?
Okay, now that we've got a feel for the subatomic world, all those tiny particles and how they interact, let's zoom out. Let's see how all of this actually shaped the vast universe we see today. We'll talk about the Big Bang, the formation of the first elements, and how all those mysteries of dark matter and dark energy play out on a cosmic scale.
From the smallest to the largest, this deep dive keeps getting better and better. All right, so we're back for more deep dive. It's amazing we've gone from electrons to quarks, from the standard model to, like, mind-bending theories like string theory. It's incredible to think about all the stuff happening in the universe at these tiny scales we can't even see.
It is. And now we're going to take all that knowledge we've built up about these tiny particles, and we're going to zoom out, like way out, to the biggest scale imaginable, the entire universe.
Okay, cosmic perspective time. I'm ready. You mentioned the Big Bang before, and it's just mind-blowing to think about, right? The whole universe, all those billions of galaxies, starting from something smaller than an atom. So where do particles fit into that story?
So in the first, fraction of a second after the Big Bang, right, the universe was insanely hot, insanely dense, and you couldn't even have atoms. It was just too chaotic. It was all just pure energy, pure particle chaos.
So, like, cosmic particle soup. What kind of particles are we talking about here?
All those fundamental particles we've been talking about, quarks, leptons, bosons, they were all there, zipping around at almost the speed of light, constantly colliding, interacting.
And then as the universe expanded and cooled, these particles started to, like, team up, right?
Exactly. So as things cooled down, the quarks, they started binding together, forming protons and neutrons. And eventually the electrons joined the party, and you get the first atoms forming, mostly hydrogen and helium at that point.
So that process, that's what created the first elements in the universe, the elements that make up, well, us, the Earth, the stars, everything. That's incredible.
It is. We are all made of stardust, literally. And as the universe kept expanding and cooling, gravity started to do its thing, pulling matter together, and eventually you start to get the first stars and galaxies forming.
It's amazing to think about how all these tiny particles we've been discussing actually played such a crucial role in shaping the universe as we know it. But you mentioned earlier that the standard model, it doesn't explain everything, right? Like dark matter and dark energy. Where do they fit into all of this?
Yeah, that's where things get even more mysterious, for sure. So we know that dark matter exists because of the way it affects galaxies, its gravitational pull. It's like this invisible glue that's holding galaxies together, influencing how they rotate.
Right, so it's matter, but it doesn't interact with light. We can't see it, but we can see how it affects things around it.
That's a great way to put it. It's kind of like, imagine trying to understand the wind. You can't see the wind itself, but you can see how it makes the leaves rustle, how it makes flags wave.
Okay, I can picture that. And dark energy, that's the one that's making the universe's expansion speed up.
That's right. It's like a cosmic anti-gravity, pushing everything apart faster and faster.
So we have this universe that's mostly made up of stuff we can't even see, and it's not just sitting there, it's expanding, and it's doing it faster and faster all the time. That's a lot to process.
I know, it's pretty wild. And the true nature of dark matter and dark energy, that's one of the biggest unsolved mysteries in physics right now. We have some ideas, some possible candidates, but the definitive answer is still out there.
Well, speaking of mysteries, what about black holes? Those are some of the most, I don't know, extreme and fascinating objects in the universe.
Black holes are definitely extreme. They're regions of space-time where gravity is so strong that nothing, not even light, can escape. And they form when massive stars collapse at the end of their lives.
So all the matter in a star gets crushed down into this infinitely small point.
Yeah, we call that the singularity, a point of infinite density. And around it, there's the event horizon, this boundary of no return. If you cross the event horizon, there's no coming back.
It's both terrifying and fascinating at the
Yeah.
same time. It's like a giant cosmic vacuum cleaner sucking up anything that gets too close.
That's a good analogy. But here's where things get really weird. Black holes, they also have this property called entropy, which is basically a measure of disorder, of information.
Wait, so these cosmic vacuum cleaners, they have information. What does that even mean?
It's a deep question, and it gets to the heart of something called the information paradox. The basic idea is that if information is truly lost when it falls into a black hole, that violates one of the fundamental rules of quantum mechanics, which says information can't be destroyed.
So where does the information go? Does it just vanish?
That's the paradox. Some physicists think maybe the information is somehow encoded on the event horizon, that surface of the black hole. Others think maybe it gets radiated back out in some subtle way. It's a mystery we're still trying to figure out.
Black holes, they're more than just cosmic monsters. They're like cosmic enigmas.
They are. And studying them, it really pushes the boundaries of our understanding of gravity, quantum mechanics, the nature of reality itself, really.
This deep dive has been incredible. We've gone from tiny particles, zoomed into the heart of atoms, then expanded out to the vastness of the universe. And it's just amazing to think about how it's all connected.
It really is. From the smallest particles to the largest structures, the universe is this amazing tapestry, all woven together by these laws of physics. And the more we learn, the more we realize just how much more there is to discover.
So what's the big takeaway for our listeners? What should they be thinking about after this wild ride?
I think the biggest takeaway is that even though we've learned so much about the universe, there are still so many mysteries left to solve. Dark matter, dark energy, the information paradox, these are just a few of the puzzles that are still out there, still challenging our understanding of the cosmos.
It's pretty exciting to think about, though, right? All these unanswered questions. It means there's still so much more to explore, so much more to discover.
Exactly, and who knows what incredible insights are waiting for us as we continue to explore the mysteries of the universe.
Well, this deep dive has been absolutely mind-blowing. Thank you so much for taking us on this incredible journey through the world of particles and beyond.
It's been my pleasure. And remember, the universe is full of wonder, so keep exploring, keep asking those questions, and never lose that sense of curiosity.
That's the perfect note to end on. Thanks for joining us for this deep dive, and until next time, keep looking up, keep wondering.